This is the sphere we build in Regent's Park. You can see it's in a plane tree. It's 5 meters in diameter, and it consists of great circles, starting with the equatorial circle, and then we build up these major rings. It's completely rotationally symmetric, so any one of those rings that are shown now can be the equatorial ring. At first we get triangles and pentagons, and then you add the minor great circles, and they cut across the pentagons and these star shapes form. Now when we built it, we didn't know what these angles were going to be, and if it was going to be built on a grander scale, it would be useful to know. It's fairly simple analysis because it's a sphere. So we get the equatorial plane, divided into 10, so it's 36 degrees each, and then we analyse with 3 major great circles a pyramid. So each side is 36 degrees because of the rotational 3-way rotational symmetry, and we just apply Pythagoras to find out the length. The radius was 3.5 meters, but it can be whatever you like. That gives you A. It's fairly labour intensive, but it's just basic. Pythagoras applied 4 times. And then this, if you imagine a plane that cuts the sphere in half, there's triangles in that plane, and that plane's important because the projection of the connector is on this plane, and there's the first angle, 31.7. So that's using a mixture of the sine rule and Pythagoras. C squared is A squared plus B squared. And there's projection, and it's times that by 2, and that gives you one of the angles that you require. Because we've got a minor circle passing through this node on the equator, we need to get one more angle, which is the angle formed by a major circle, a minor circle, so two major circles at the top and a minor circle on the base, and so this would be the base of your pyramid. Similar analysis, the sine rule and Pythagoras. So we considered a plane that the minor ring is in, and you could call it the minor disk, and that's 60 degrees. There's six nodes, 6 crossings on the minor disk. So 360 divided by 6 is 60. It's divided by 2, so we can apply the sine rule. You could also apply other trigonometric identities, but I chose to use this just to make it complicated. and this final triangle is in that projection plane. Oh, it's not in the same plane as the last one. So we cut the sphere down a different. We cut the sphere in half, and this, where you can see the 20.9, that plane is cut the sphere in half in a different place to the last analysis. There's the last angle we worked out, 63.4. There's a 20.9 will give you the times by 2 gives you the minor projection, and then some simple arithmetic we can find a 37.4. And there's the angles you need to make this Matinee connector, which is shown there, which would make the fabrication easier.